Hey folks, Todd Coburn here, the Aerospace Structures series. With this video, we're going to continue our study into classical lamination theory, and now we're going to look at how this theory is applied at a detail level. Let's see how that works. So let's just imagine we have a composite laminate that has 4 lamina or layers of 0.01 thick graphite epoxy. The layup is 0 plus minus 45, 0. And let's say that we've already determined our transformed reduced stiffness matrices for each lamina, Q0, Q for the plus 45, and Q for the minus 45. Now, we saw before, last video, how we could construct our A matrix. Remember, we're going to need the A, B, B, D matrix in order to solve, to transform stresses to strains and back again. And so let's look at how we create that A matrix. Now remember, our equation says that we're going to sum the Q bar for each layer times the Z minus Z minus 1 position. So from the bottom, the position of the bottom of the layer to the top of the layer. This is basically integrating that axial stiffness for each layer. And we also saw that we can write that more simply as the summation of the Q bars times the thicknesses of each layer. Okay? So that means our A matrix is simply, now if you have a calculator like a Ti-nspire, then, or other programmable calculator with good matrix equations, you can just store your Q bar matrix in one matrix, in one variable, your thickness of each layer in the other, and just multiply the Q times the thickness, and then sum up all of those. And this is going to show us how that's done. So the A matrix is the Q bar matrix times the thickness. You'll notice we have in this layup, we have 2 0 plies, one at the top, one at the bottom. And since they're only multiplied by the thickness, we can just use a 2 times the Q bar times the thickness. Then we deal with our first plus 45, which is that 45 Q bar matrix times its thickness, plus the minus 45 Q bar times its thickness. We now sum these up. With your calculator, this is going to have the effect of multiplying all pieces of the first matrix by 2 and by 0.01, or by 0.02. The second matrix is multiplied by all elements times 0.01, the third by 0.01. Then you add up each individual element of the matrices, and that gives you your Q bar, your A matrix, which, because of the units that I used above, we see that this is units of kips per inch, is the units for that matrix. Now we could also express this in pounds per inch or whatever. You need to be a little bit careful, and this allows us. Now the problem is if you're using like a program like MATLAB, and sometimes with our calculators, is it can be hard. If we use the like just show this in pounds per inch, these numbers are going to be so big, our I without little commas to separate the 3 digits, it gets hard to recognize the magnitude of the number. So whenever the numbers get big, it's often better to express it in a different unit. So if we're talking about E, the modulus elasticity, often in US units we show that as MSI. And if we're talking about running loads for like this running stiffness, kips per inch, actually kips per inch allows us to quickly spot the magnitude, 600 kips per inch, 131 kips per inch. So the choice of units can make it easier. Now the problem is when we start operating on this matrix, we don't want to forget what units we expressed it in, so we don't introduce an error into our analysis of like an order of 1,000, which can be a problem. Okay? So once again, we said this, we've got kips per inch, and then we multiply by strains, inches per inch. That will remain, anything that's multiplied by will remain as kips per inch. Let's take a look at how we do the B matrix. We're going to do that in a similar fashion. We've got the same lamina here, or laminate, These are the same Q bars, and now we can look at the equation for the B matrix, which we saw was given like this. However, we also saw we can write it more simply as the Q bar times the thickness of each of that same lamina times the Z bar of that lamina, and then you add them all together. Now remember, we're starting from the top, so C0 is the very top of the laminate, Z1 is the bottom of the first layer, and so on. And Z bar is the midplane dimension measured from the midplane of the laminate with positive acting downward. So these are our Z bar parameters, and if you're doing this analysis, it is useful to first sketch the composite laminate, to sketch the dimensions you're going to be using, and then compute them, and then look to make sure they make sense. We can see Z bar for the topmost element is up here, since we have 4 layers, and each ply is 0.01. The Z bar of layer 2 is minus, because it's in the negative positive direction. It's minus half of that thickness, so instead of 0.01, it's 0.005. And the other one is 1 thickness, 0.01 in the negative direction, plus half of thickness, 0.005, so that one's at minus 0.015. On the other hand, the third layer is half of a thickness positive, and the fourth layer is 1.5 thicknesses positive, as we see here. Once we have this, all we have to do is take each Q bar, multiply it by its thickness, multiply by its Z bar, and then sum up the layers. You'll notice layer 1 has a thickness, and it has the negative 0.015. Layer 2 has the Q bar, same thickness, and the plus 0.015. So that's that first term, has both top and bottom layers. Then we have our plus 45, and we have our minus 45. We just sum these up, and we find this B matrix to be this. And we see now for this matrix, because we're multiplying that Q bar, which was written in terms of MSI, times a thickness and a Z parameter, we see that we now have units of pounds. We could have also expressed this as kips, but then we would have had all decimal entries, and it's a little clearer to see the magnitude. Okay, now when we multiply this puppy, we're going to be multiplying it against the curvatures, then that will be pounds per inch. And if we multiply it by strains, it will remain pounds. Okay? All right. And this is a little warning about mixing units. Whenever we're reporting numbers with different units, it's a little dangerous. We've got to be careful. The D matrix, we're going to start with the same laminate again. We have the same Q bars. And this is our equation for the D matrix, which we saw could be written more simply as the summation of the Q bars times the corresponding sum of the TZ bar squareds plus the T cubed over 12. This first term is taking that stiffness matrix, and it's actually giving us the additional stiffness, bending stiffness, due to the area of that not being at the centroid of the laminate, or the midplane of the laminate. And the second term is due to the bending stiffness about its own axis. Now, remember, when we're dealing with only a laminate, because those laminates had no, we gave them no ability to carry moment, the laminate itself, if you only have one, has no bending capability just by our assumptions. However, once we stick it in the laminate, even though we're still going to treat it as having only axial stiffness, axial and shear stiffness, we now are accounting for the additional stiffness due to its bending using this equation. So, as before, it is useful to use the same sketch we had where we have the thicknesses and the Z bars all identified, and then calculate this second term, this TZ bar squared term plus the T cubes over 12 term for each and every layer. As you see here, we see it for the top layer, the second layer, the third layer, the fourth layer. If you are a student, it's critical that you both sketch that element, that laminate, identify those Z positions and the thicknesses, and then to work from that sketch when you're computing these, and then to check and think about what you've written before moving onward and investing a lot more time with an erroneous answer. Students notoriously makes a lot of mistakes because we're nervous, we're overthinkers, that's why we're engineering. And then when you get out in industry, you're going to find the same problem, except nobody's checking your work, nobody's grading your work. It's rare, even though it's good to have a program where everybody's checking each other's work. There's actually very few companies that do that very well. And so you need to manage your own work, check your own stuff, and part of that is sketching, identifying, showing your work. Even though when no teacher is checking you, by showing your work, it makes it easier for you to evaluate what you've done and see if it's accurate, which is a critical skill for success in engineering and for safety in engineering. So continuing on, now that we have the second term computed for each and every laminate, and it looks like, okay, these numbers kind of make sense. You'll notice the second and third ply have the same value, as do the first and fourth, because of the layout of this laminate. That all makes sense, which helps to confirm that we may have a correct solution. We then go and we see, okay, so the first and fourth layer are the same, so we can just use a 2 and we do that. And then we have the other two terms, which we apply this way. Now these ones have the same second term, but they have different Q bars, so we can deal with it like this. Now we sum those puppies up, and we get our D matrix, which in this case is in units of inch-pounds. Now, when we take that, once again, we see that we've switched units, so we got to be a little bit careful. And when we multiply this by the curvatures, that 1/inch value, we're going to now be back to pounds for this matrix. All right. Once again, we're warning about the mixing units, and when we move those forward, to make sure that we have checked our units to make sure that they're meaningful and haven't introduced errors. So we saw how to calculate the A matrix. This was our Q bar. And now if we want to calculate the ABBD matrix, this actually is misidentified. We're finding the ABBD matrix now, which is our big mamba jamba matrix, where we're going to use to relate stresses to strains and back again. That's just that augmented matrix of the ABBD. So if we put these together, we've got the A matrix, we've got the B matrix and the D matrix, which go together like this. You'll notice this upper 3x3 is the A matrix. The one to the right and below is the B matrix, and the one at the lower right is the D matrix. That constructs the ABBD matrix, which you now can use to relate stresses to strains. Now, we've been talking about units. Let's think about this a bit further. The A matrix was in pounds per inch. We're going to multiply it. The A matrix gets multiplied against the first 3 strains, which are in inches per inch, which means the A matrix multiplied by inches per inch is going to remain in units of pounds per inch. And that's going to give us the running loads, pounds per inch. That makes sense. Stand by. Now with the B matrix, that was given in pounds. We had the units were pounds. Now we've got 2 B matrices. We've got the upper right B matrix and the lower left B matrix. The upper right B matrix is in units of pounds, and it gets multiplied against the curvatures 1/inches. So when we take units of pounds, multiply by 1/inches, we're going to end up getting pounds per inch, and this is going to give us those, it's going to contribute to those running loads, pounds per inch, in the first 3 entries of our loading matrix. The lower left B matrix is also in units of pounds, but this one gets multiplied up against the strains, inches per inch, which means that that is going to end up with units of inch-pounds per inch, which matches the moment values of loads from the lower portion of the loading matrix. The D matrix, which contributes to those same values, is in units of inch-pounds, and that gets multiplied against the curvatures 1 over inch. So in the D matrix, inch-pounds gets multiplied by 1 over inches. That's going to end up in units of pounds, or inch-pounds per inch, which matches the units of our moments. It matches the units of the B matrix that was multiplied by the strains. It's added together to create the total value of moments, which are given in units of inch-pounds per inch, because it's a moment per unit inch. It's a running moment. So even though we had mixed units coming in, we have units of pounds per inch, units of pounds, and units of inch-pounds. Each of these submatrices are multiplied by either strains inches per inch or curvatures 1 over inches, and this gives us units of pounds per inch for the running loads and inch-pounds per inch for the moments. So everything worked out fine. Now all we've got to do is make sure that we're consistent. Now when we showed these matrices, we were earlier showing some of them in units of like kips per inch or things like that. But here we need to make sure that we're consistent enough, even though we have pounds per inch, pounds, and inch-pounds, and our strains are in inches or 1 over inches, inches per inch or 1 over inches. So now we see everything in this matrix is either pounds or inches, even though we have mixed units of pounds per inch, pounds, and inch-pounds, with inches per inch and 1 over inches. This may seem like a trivial matter, but it's critical that you understand this and you harness these equations correctly so you don't introduce error into your academic work, and even worse, error into your industry work, when people are going to be in the air when they find out whether or not you made a mistake. All right, so now that we have constructed the A matrix, the B matrix, the D matrix, and the ABBD matrix, we're ready to use these and to find out how to calculate our running loads and moments. Now remember, these are our running loads and our moments given in terms of inch-pounds and inch-pounds per inch. We know that this relation is true. We can calculate this in as written to calculate running loads and moments from given strains, or we can use this, the inverse of this relation, to take the running loads and moments to calculate the strains. That's actually more common. Let's just say we're given a body coordinate strains as shown up here in our given of 0.002 inches per inch, 0.005 inches per inch, and 0.003 radians per inch. And don't forget, your curvatures need to be in radians per inch, not degrees per inch. So we plug in our ABBD matrix, multiply it by our strains, and that will directly give us our running loads and moments, which we find this. Once again, don't forget here, these upper 3 values are pounds per inch now, and the lower 3 values are inch-pounds per inch. Got that? And all these are in body coordinates. So we had body coordinate strains, that gives us body coordinate loading. All right, well that makes sense, at least so far. Now, let's think about this. Now we have our ABBD matrix, and this is actually, I'm showing the inverse of that matrix, and your calculator can perform that quite nicely. Let's say that instead of what we had last slide, let's say we're instead given the running loads and body coordinates on the laminate. That's more common. We're often going to be calculating or being given the loads, and we're going to need to find out what are the stresses in the lamina. Before we can get stresses in the lamina, we need to calculate the strains at the midplane of the laminate. So we can use these in our equation. Here's how it works. We start by, regardless of what we want, we're going to start by getting our midplane strains. So we use this form of the equation now, and we can write it this way. This is the inverse of the ABBD matrix multiplied by our running loads and moments, and that will give us our strains and curvatures in body coordinates. And when we perform that multiplication, we find out the strains. Now, in the last problem, we were given these strains and we calculated running loads. In this problem, we're giving the running loads and we're calculating the strains. this wouldn't be, we wouldn't go back and forth like that, but this is just showing you one way these equations are used and the other way these equations are used. And since we used similar, the same values for that, we see that these match, give you the same results. Now, once again, don't forget here, your running loads, it's more common to be given running loads or to calculate running loads and then to go and calculate what are the midplane strains. Now, as I said before, we're generally not going to stop with midplane strains of the laminate. We generally don't have allowables for midplane strains for the laminate. What we need to turn these into is the lamina stresses. And in order to do that, we're going to first need to calculate these midplane strains and curvatures, and then we'll use those to calculate the lamina, the strains in each lamina, and from those strains we can calculate the stresses in those lamina, and then we can transform those into material principal directions, which is generally where we have our allowables. Let's see how that works. All right, so now that we have the running loads and moments, we're now going to determine, and this is misidentified because we're now going to identify the strains at the midplane of ply 1. Generally, we will maybe checking all of the ply strains that will be in stresses, but this is going to show you one piece of that. So remember, this is our equation for calculating ply strains, lamina strains, from the midplane laminate strains. We just take the midplane strains plus the Z position of our lamina times the curvatures. And this is actually, should be the Z bar. This says Z, it should be Z bar. We're going to take the midplane strains plus the midplane dimension of our lamina. Now, if we wanted our strain at the top of the first lamina, we could use the Z minus 1 of that. But we generally are going to have the stiffnesses and the allowables are valid at the midplane of each lamina. And so we're going to want to plug Z bar into this. The Z is just a general thing we need to put in Z bar to get those values. So here you see we put in the midplane strains that we developed. We put in the midplane curvatures that we just calculated on the last slide. And because we're talking about ply number 1, which Z bar was at minus 0.015 because it's above the midplane and positive is pointing down, we can just plug this in and this will give us those strains. Once we have these strains, we then can convert those to stresses and transform them. So that is our basic approach. Now, you'll notice we just got to that first ply, and actually we would go through this process. Once we get the midplane strain for each lamina, we then turn those into stresses for the lamina, and then we transform them to a material principal direction. And then we do that again for the second ply, for the third ply, for the fourth ply. Once we have all the stresses in the principal material directions for each and every ply, for each lamina, we then compare that to the allowables for that lamina using an appropriate failure mode like the max stress failure criteria or the Hoffman or the Sahil or whatever. Got it? This is a little slide that walks us through the solution procedure. We're going to get the properties of each lamina. We're going to use those to calculate Q. We then transform Q to get the Q bar. Those two steps were not shown in this video because we were assuming we'd already done that using our earlier material. We're going to use the thickness of each ply to determine the top and bottom of each lamina, remembering that we have a positive Z defined downward from the midplane of the laminate. And before we do that step, I should add a step here. You should sketch your laminate. Sketch it top to bottom, number the plies 1 at the top to the last one at the bottom, and then identify your thicknesses on each, identify your Z, so Z minus 1 is the top of the laminate, Z1 is at the bottom of the first layer, and so on. Then use those T's and Z's to calculate your Z bars for each laminate, which means you're going to get the mid-plane position of the first, second, third, and so on layers. Once you have all that information, you're ready to proceed. We use that Q bar and our Z parameters, Z bar parameters, to get our A and B and D matrices. We then construct the ABBD matrix. Then we use our running loads and moments, or our strains, typically the running loads and moments, to calculate the midplane strains and curvatures using this equation. We then use those midplane strains and curvatures with the Z bar of the lamina to determine the lamina strains. Remember, this is Z bar, not just Z. We then use the lamina strains to determine the lamina stresses by using Q bar. This transforms from body coordinates of the lamina for strains to body coordinates for stresses in the lamina for each and every ply. We then transform those stresses into the principal material directions using our transformation equation for each and every ply, being sure that we're using the T for each ply with the strains of that ply to get the material principal directions. We then use whichever suitable failure criterion. If we're using maximum stress, we're just going to compare each value, write a margin of safety on each value against its allowable. And if you're using Sci-Hill or Hoffman or something else, we're going to use those failure criteria to plug in all these values and see how it relates to the allowable. That is classical lamination theory. We saw how to do it last lecture. We now went through and practiced doing that. And I encourage you to practice this as much as you can before our next lecture, when we're going to learn how to deal with hygro-thermal loads, which means when we have temperature-induced stresses and thermal-induced stresses. Now remember, temperature induces strain but not stress unless there's a constraint. And pretty much by definition, when we have a composite made of multiple materials or stiffnesses that are different in different directions, any attempt to strain is going to introduce stresses between the different parts of the laminate. And same thing with moisture, which is going to induce strains in a manner that's analogous to temperature. That's going to introduce stresses when each lamina tries to strain in a different manner and it's resisted by the other elements of the laminate. So stay tuned, practice this, enjoy.